Yeah, happy that we have our Mercator Fellow today for the seminar. It's Rupert Klein. As you see there, he's a professor from the Freie Universität Berlin. And there he's in the Institute für Mathematik. So sounds very mathematician, right? Mathematician-like. But I know that your education, you're an engineer, mechanical engineering education. So, and it's also the reason that Rupert is known to bridge the gap between application to mathematics. And he was also speaker of the SFB in Hamburg, in Berlin, scaling cascades and complex systems, where there was collaboration between mathematicians and metrologists, also other disciplines, and also before he was coordinating Matchström. Maybe some of you remember that. It was a similar program, collaboration between metrologists and mathematicians, also quite successful in engineering and even engineers, right? And yeah, and this topic is kind of related, right? Thoughts on machine learning, and we're happy to have you here.
Thank you very much for the invitation, Peter and Carsten. Disclaimer to begin with, I'm not a developer of machine learning methods. I'm not a user of machine learning methods. I have observed the scene around myself and I got concerned at some point, and some 1.5 years later, I thought, no, I have to tell people why I am concerned. And now, if you don't run away now, you're going to be my next victims. So it's thoughts on machine learning, and I'm borrowing insights from Jinchao Xu, who is a numerical analyst by most of his career, but he has recently started looking into approximation properties of deep neural networks together with his co-workers. And I also will report a bit more extensively on machine learning technology, entropy-optimal sparse probabilistic approximation, and versions of it developed mainly by Illia Horenko, who brought in the main ideas, and he has now a couple of people working with him, in particular also in many applications. And I've given this talk last time in Bad Orb at this very nice workshop, Mathematics of the Weather, which Jürgen Steppeler has launched some 20-something years ago, and it's still going on every 2 years. It's a really nice thing. If you ever stumble over an advertisement, I recommend going. Okay, now this doesn't want anymore. Too bad. Okay. Something is funny. Now it works. Okay, motivation of this comes from El Nino prediction. And the idea is to find a function that, given sea surface temperatures and some other variables that I will discuss in the area of the Pacific around the equator, to predict whether n months down the road, a certain index, the Nino 3-4 index, is beyond 0.4 degrees Celsius or not. The Nino index is the difference between a long time average of sea surface temperatures in some area covering about the reddish colored part in the plot. And you take the difference between this long-term average and a 5-month average around the time where you want to then predict or indicate whether it's an El Nino or not. And if this difference is in modulo is bigger than 0.4 degrees, then you have an El Nino. If it's less than minus 0.4 degrees, you have La Nina, and in between you have nothing. And so the idea is to find a map that takes essentially information from sea surface temperatures and ocean temperature distributions at time now, and predict whether n months down the road you will have an El Nino or not. And you would like to interpret this as a probability of appearing, so it's going to be a number between 0 and 1. Why is this of interest for a machine learning application? Weather prediction, we know, works about 10 days ahead, and then it becomes sort of uncertain and falls apart a bit later. Climate modeling, by definition, addresses timescales of something like 30 years and the statistics of the weather. So by default, or by definition of weather and climate research areas, a prediction of 10 months or 16 or 20 months ahead is not in the range that weather forecast models are designed for, and neither is it in the range of what climate models are made for. So physics-based models, so far, we don't have any of them that are specifically tuned or adapted or designed to make this intermediate timescale prediction, which, however, is extremely important for example, for the farmers who live in this area and would like to know before the next season has started what they should order in terms of seeds and so on and so forth, and how to manage their farms. And now the idea was Ham and al. Nature 2019 to use a machine learning tool, neural network technology, to try to take data from today. They took just sea surface temperatures and try to predict what happens n months down the road. And they found that the quality, or if you wish, some kind of skill score they achieved for 16 months prediction ahead was comparable to what physics-based models have been achieving over only 10 months. So it was quite a step ahead. 6 months more is non-trivial in this context.
Physics-based model, you mean a climate model, which is run forward, coupled model, ocean atmosphere model? What is physics-based?
Yes, I guess so. That's what Terry O'Kane told us. He's at the throrough Center in Australia, and he's been involved in that. Anyway, so then Illia Horenko and his team, this is the paper Vecchi et al. Neural Computation 2022. They took that as one of their test cases for the sSPA method that I mentioned earlier, and said, let's try that with our technology and compare with others. And what they took, and this is why I'm describing this here in a bit more detail, they took sea surface temperature data, but Terry O'Kane had the EOFs, the empirical orthogonal functions, available for these distributions, and they took the leading 100 EOFs of the sea surface temperature, and they also took the leading 100 EOFs of basically this temperature, vertical temperature stratification along the equator in a vertical slice. So these were the input data for learning a function that does this, hopefully does this kind of prediction. So they took this in addition to the information Ham et al. Took into account, because Terry was interested in finding out whether this deep ocean temperature distribution has any impact in improving the prediction quality. So far, so good. Now, let me make a few principal remarks about what in machine learning is often being tried to do. What we have at hand here is, for simplicity, let's say we look at Ham et al. And we just take sea surface temperatures. We have 100 degrees of freedom. That's 100 amplitudes of EOFs that are the input to the function to be learned. And the output is a number between 0 and 1. So we're trying to construct a map that goes from a 100-dimensional space into the reals. Now let's look at how many data we have available in this context. It is about these 100 degrees of freedom measured every 6 hours over 30 years. That's what they took from the era 40 data. And when you do that, you get essentially 5 million individual EOF amplitude data. So 5 million numbers to learn from. Is that big data? Is that small data? That's the question here. And 5 million, that's a substantial number of numbers. But let's see what we're trying to learn. If you take a map from R100 to R seriously, and you just want to, for example, imagine how complicated can it possibly be. Take the dumbest function I can think of that's non-trivial in 2 dimensions. It would be the bilinear function on the unit square. In 1D, it's the linear function on an interval. In 2D, it's the bilinear function on the unit square, just to get an idea of how complicated it's going to be. In 3D, it's the trilinear function on the unit cube, and so and so on and so forth. Now take the unit cube in 100 dimensions and check how many numbers do you need to nail and provide in order to uniquely define this multilinear function on the unit cube in 100 dimensions. Result, 10 to the 30. That's 10 to the 24 more than we have up here. We cannot even store this number on any of our computers, this number of real numbers, not to speak of doing anything with them. It is completely clear that in 100 dimensions, a function that really taps into all the degrees of freedom it has in 100 dimensions, we will never be able to represent it on any computer anytime soon, period. However, we all know machine learning works wonders. It does amazing things. There's plenty of examples by now. The message is this can work on today's computers, given these constraints, only if behind the scenes there is some drastic dimension reduction, which an unknown entity has imposed on the function we like to learn. But of course, that entity hasn't told us what that dimensional reduction looks like, what's the logics of it, and how does it come about. We don't know about it. We just cross our fingers and say, maybe there is a dimension reduction. Let's use machine learning to see. And then when it works and you get a reasonably good match between your learning and training and testing data, etc., and so on and so forth, the whole galore, then it can either you're lucky, or the function really that you're trying to learn has only a reduced dimensionality. It represents some subspace of this very high dimensional space of functions we have in 100D. And I don't need to say that, emphasize it again. Obviously, 5 million data with respect to this is a tiny, tiny, tiny data problem, and not a big data problem. So methods that are originally designed to do big data analysis aren't designed for this. Nevertheless, they seem to work sometimes, but this is by luck. And now I'm moving on, yeah?
What do you mean by big data? Big data means that you have more data than parameters to fit? Or is it that just the number of the data points you have?
That's the whole point. The big data, in my understanding, is a situation where you have a function that is very well approximable by the data you have, and you know that a priori. So you have like 100 plot dots in a two-dimensional diagram, and you want to fit a regression curve, right? So you need two numbers, two points in the plane in order to fix the linear curve, but you would like to have like more than 10, rather 100 data points in order to get a good and secure estimate of the accuracy of your data. So in that sense, yes, big data is you have a lot more data than you have degrees of freedom. Okay, now that said, that's a big warning. We should all be aware of this when using machine learning tools on problems like this. Let me say a few more things about neural networks. The notion of interpretability and explainability of artificial intelligence tools is everywhere. It's being discussed. It's an important issue. I appreciate that many people look into this question. A solution is not there yet. I can safely claim that. We don't have a machine learning tool based on neural networks that is in detail explainable in the sense of a scientific explanation. It's not there. As a mathematician nowadays teaching analysis or calculus, the first thing we tell our students when we explain to them what is a function, we tell them a function is a map from a domain to a range. So you give a domain of definition of the map, and you give a range where the function is landing with its output, and then you also give it the functional form of the mapping between the two. Why is it important to have a domain of definition? Well, you don't want to feed into your function a number that it doesn't understand. Right? So if you have a function that has as an output only the real numbers, and it solves an equation, and then you give it the wrong the input, it will want to compute a complex number, but it cannot, because you gave it a number outside of its domain of definition. Now, neural networks do not give us the domain of the learned function in general. You get a map, that's all you get, and then supposedly it's applicable in your entire RD space. Nobody tells you, no, you only need to are allowed to look at this kind of subdomain of your data's input space. That's a big problem. And I think that that's also why adversarial attack issues are big in neural networks, where you can take a picture of a cat, change one pixel in a judicious way, and suddenly the neural network thinks it's a dog or a race car. It all happened. There is plenty of examples, and maybe I have later time to explain a bit more why I think it happens in a bit more concrete fashion. Then they are greedy for data because they are big data methods to begin with. So in general, they're assuming I have a lot of data before I can say anything. And so that's a problem when you have a small data problem. Getting the parameters of the neural network is unfortunately inefficient because the optimization problem that you try to solve is non-convex and has all sorts of difficulties. So what people use is stochastic gradient descent methods, and those are first-order convergent and come with uncertainties and all sorts of things. And they are extremely inefficient when you compare, say, first-order methods in the classical numerical analysis field to higher-order convergent methods like Newton. So they are expensive, and it's not for nothing that the big companies that do AI in the US now want to buy little atomic reactors in order to feed their machines. This is all not a joke. This is actually very serious stuff. So they are inefficient in learning. Not in the evaluation. Once you have learned it, the evaluation is cheap, but the learning process is really expensive. Yes, and then comes this consideration by Jin-Chao Xu and colleagues, who said, rectified linear unit activation functions are used a lot because you can relatively efficiently do the training, and you understand mathematically already quite a bit about them. Rectified linear unit is, for those who don't know, is a function that when I input x into what is called a neuron in this context, one single neuron is a function that gets a scalar input, a number, and puts out a scalar number, right? And so the rectified linear unit is simply this function. It is 0 all the way up to 0, and then it is x for x larger than 0. So it's this ramp function. And it turns out when you take this as what is called the individual neuron or the activation function in the deep neural network, it is known that what you get in the end is a function that is piecewise linear on polygons in your high-dimensional space. So here I've said, but then we should be able to represent with rectified linear unit deep neural networks a simple ansatz function, the basic ansatz function of a finite element method, of the linear finite element method. Or do the same in 2 dimensions. You have this hat function over a polygon. And then you can extend it to higher dimensions. And they analyzed this in all detail. The conclusion is, yes, you can do that. You can exactly represent the basis functions from finite elements. But when you go to high dimensions, it turns out the number of degrees of freedom you need, 3 parameters in your neural network that are to be trained, in order to do that is when you have a full piecewise linear function on a finite element triangular grid in d dimensions, the number of degrees of freedom you need is the number of nodes. That's an obvious parameter. The bigger the grid, the more unknowns. The number of nodes times the dimension of space times a number kappa larger than 2 to the power of the dimension. Remember, 2 to the power d is 10 to the 30. There is a big problem here that you would say, well, but we aren't doing finite elements, right? We do this more elegant crossing of lines that are generated by the activation functions, and this is why this is not relevant. But I tell you, it is relevant for the following reasons. You may have functions that look like a map of a certain functional form in a part of your domain, and like a very different one in another part of the domain. If that's the case, you need to shield one of the parts of the domains from the other, so that your lines you're creating by the activation functions, which are basically the edges of the polygons, right? The edges of the polygons are defined by planes. Unfortunately, the planes extend to infinity, so they crisscross all over the place. And in order to shield one region from the planes you created in the other region, you need to do this covering, which leads to that bad factor here. So in a somewhat trivial case, already you stumble over this obstacle. If you do it with finite elements straightforwardly, you just need n times d plus 1 degrees of freedom to represent such a function. Okay. Enough of the DNN bashing. Let me say something about the method introduced by Illia Horenko and company. Entropy optimal sparse probabilistic approximations for this supervised learning. They have done it for many other machine learning tools by now, so this is just an example of how it works. And the beauty of this is, and I don't apologize for it, the whole method is on this screen. It's this one formula with this definition up there, and that's the method, except for solving the optimization problem, which I'm going to get to on the next 2 slides. But because it's only on one slide, I can explain to you each and every ingredient of this formula, and I will do that now, to convince you that this is not a black box, where basically behind the scenes very complicated things are being done that you then need to chase down by explainability studies. With this method, you will understand at the end of this transparency what it is about and what each ingredient does. Let me try to convince you. So what we do is we are trying to find 4 matrix parameters, S, gamma, W, and lambda, such that this functional listed here is minimal. in this expression here, capital X is all our data points, the inputs to the function we're trying to learn as found in the data. The pi delta t here is the real probability of having observed El Nino n months down the road. So this is 0 or 1, because we are looking at era data and we knew when there was an El Nino and when there wasn't any. So we can decide 0 or 1. So the probability we can assign to learn is 0 or 1, whether an El Nino was happening down the road, n months down the road or not. So this is the input data, arguments to the function and the targets that are labeled. This is why it's supervised learning for our learning process. The first step, and remember, we have a big problem with high dimensions. We want dimension reduction. The first step in dimension reduction is what is done in many machine learning methods, namely to do some kind of clustering. Try to find in the cloud of X points, so this is in a 2D plane, a qualitative sketch. The X's here are represented by all these points. This is supposed to be our input points into the function, the data that we have as inputs to the function. And we try to represent these X's by introducing reference points in the plane. And this matrix S is just a very simple thing. It's a matrix that has as its columns the coordinates of the reference points. Okay, so in our 2D plane here, it would be 3 points. So the matrix has 3 columns, and each column has two coordinates, namely the coordinates in X, Y in the plane. So the S matrix is representative of the reference points. Okay? Now we try to approximate or get as close as possible to the data points by convex combinations of the reference points. What does that mean? To get to this point, I take alpha red times these coordinates of the red point, plus alpha blue times the coordinates of this point, plus alpha green times the coordinates of this point, and I shuffle alpha red, blue, and green such that I land as close as possible to this data point. Now, mathematicians will know with this example, in 2D with 3 points, we can actually reach each point exactly, no approximation made. But of course, in higher dimensions, this will not always be the case. But now, the gammas here, the gamma is a indexed D and T. It's the convex combination weights. So if I have 3 columns, then each column in S, this is the reference points, each column of the gamma matrix has 3 values in it, which are the values alpha red, alpha blue, alpha green. This is the convex combination weights, which for each data point, xdt, for each data point, we try to find the best values of gamma to get us close to that point, given the chosen reference points. So we are trying to approximate our data points. Yes.
Do you have 2 indices for X?
2 indices.
2 subscripts?
X has D subscripts. This is a whole vector.
And T? What is then T?
T is the index for the data point. It goes from 1 to 5 million. No, 5 million divided by 100.
What? D is dimension and T is
X
time.
For a fixed T, X is the vector of inputs. So this would be, in our example, 200 degrees of freedom from the sea surface and the ocean. T is the time series.
Time, okay. Yeah,
so we are thinking of, at a fixed T, we get one long input vector. This is our 200-dimensional thing. And this is the time series, in our case, that we can follow through. So it's as many points at which we have the measurement of the sea surface temperature and so on and so forth. That's the T.
And for each time you make this reduction or this bracketing, and then you come close to the point for each time.
The D here is again the index for the D dimensions of the space vectors, in this case of the representative vectors. The T is the time index. So for each T, we have one column of gammas in order to approximate the X vector at that time. Does that answer the question?
Yeah.
Okay, so for each time point, we have one column of gamma values. So this is why gamma is a matrix. For each time point, you have the convex combination weights and you all list them in columns.
Question is, why do you do this?
Well, we just collect our approximation and dimension reduction scheme. I'm just explaining right now what we do, and then we get to other things later. But now, obviously, we are trying to do this here at first glance in the Euclidean distance squared. We just take the component-wise differences of the original input point and the approximated input point, take the square of that and sum it over D. That's the Euclidean distance between the approximated point and the real point. At first glance, I'm saying, and then we actually want to have a good average of this error over all the time steps. So we collect the Euclidean approximation errors over all the time steps. And we want that to be small, and then we have a reasonably good approximation of our data points by a few reference points. But now comes the issue of, well, we knew from my previous considerations that 200 dimensions is way too much. And if the thing is to succeed, there has to be some kind of dimension reduction behind the scenes. Let's make the hypothesis that, in fact, some of the EOFs that we are collecting are not as important for predicting El Niño as others. In order to map that into a mathematical formula, we say some of the D errors, the component errors at index D, are less important, therefore in the error measure get less of a weight WD than others. So we now have a distribution over the dimensions with numbers between 0 and 1, that's the WDs. They all add up to 1, so it becomes a probability distribution. And when the WD is close to unity or larger, it means in the end, after everything, we have learned everything, this D's component is actually important to minimizing the approximation error for a Niño prediction, whereas those with WD very small are less important. You can allow yourself a big error here without changing the result of the prediction. So this would be a pre-selection of importance in the dimensions. And it's very clear how the system approaches this problem of selecting what's important and what is not. Okay, but now we don't want to throw away dimensions lightheartedly and just say, okay, this is not so important, but this is more important. So in order to have a distribution of the weights that's as unbiased as possible, we take the notion from information theory of the Shannon entropy. The Shannon entropy basically of a distribution tells you how equally distributed is your distribution. If you do put no constraints and you just have you only know a probability distribution is given, and you want I always forget, minimum or maximum, the maximum Shannon entropy, then actually the analytical solution is they're all the same and they're 1 over capital D. Like the dice, the standardized dice has maximum Shannon entropy. It's unbiased. Now, if you put the Shannon entropy as a constraint and you say, I want this error measure to be small, but under the condition that still the Shannon entropy is a penalty. It has to be as large as possible. So if I'm having too narrow a distribution in the W's, this term is going to beat my goal of minimization. So you balance the bias in your distribution against the error that you're allowing yourself in the approximation of the data points. If you put this as a penalty, then you get the broadest possible, most unbiased distribution of the WDs, which still helps you to reduce the number of important dimensions that you actually want to keep in the end. Okay, so this was the S, the gamma, and the W, and what's left to explain. Yeah.
Is this like that you want to penalize the complexity of your fit?
No, you want complexity if you want. So you want to prohibit the system from inadvertently falling into this is the one value that you need to keep.
Yeah,
right. So you want to be.
Would argue the opposite. I would like to have a simple model, not the most complex model. Because with complex, you can fit everything.
But if you do not do that, you might get incidentally good results, and you might miss some of the values of the EOFs that still have some certain importance in the problem. And that's what you want to keep. You can go after the fact, and I will explain that later, and say, okay, after I have learned what the WDs are, I can test whether the ones that have a significant large value are really the important ones, whereas the others are unimportant. You can test that after the fact. But before that, you want to be not prejudiced in some sense. You want to disallow the system of making prejudices. That's interpretation. We'll get to that. Okay, so what's left to do is to approximate the 0 ones, the quotes exact probabilities of El Niño occurrence. And this is done by simply assigning to each reference point a value of this probability called lambda. So we have a lambda red, lambda blue, lambda green. And then the convex combination at time t of these lambda values with the combination having been used for xt is my best estimate for the probability that's to be predicted. This is nothing but a piecewise linear function on simplices. It's a finite element approximation, if you want. Interestingly, Illia proved that after the fact, when the paper was already basically written, he put an appendix and proved, and by the way, when you do this minimization problem, what you get as a result is a piecewise linear function on simplices, which wasn't trivial to begin with. It wasn't clear that other reference points out here would be automatically out the door. But this is what it is. So it's very easy. You take the lambda values, which are you could interpret them as the probability of El Niño occurring when I'm at the reference point. And then, since you only have a few spread over space, you do interpolation in between to find the probability of El Niño occurrence somewhere in the simplices. Okay, then one caveat here. I said that you need to be lucky for the function to be low dimensional enough. So for example, the data might live on a submanifold of your high dimensional space. And why is that important? Well, if you add to this here, I haven't written it down, an additional penalty that says, don't let the distances between the reference points get to be too large. Try to keep them reasonably constrained and introduce a couple more reference points. You get this picture, right? You have more reference points. They are now forced to be close. And that means you can suddenly figure out the shape of this manifold. And when you look at this, you immediately see, there is a convex hull of this beast, which gives me the domain of definition of the function I'm learning. Automatically, it comes out of this method, which is, as I emphasized before, that's quite a feat. You cannot fool yourself saying, oh, my function is generally applicable, and I throw any data point in there. If you land out here, the method tells you I don't have reference points around me that are valid anymore. There's no simplex in the vicinity that I have learned from, so I cannot give you an answer. Okay, then, well, I said the problem must be solved in the end. When you look at the functional in its original form, turns out it's a convex, non-convex optimization problem, so it's not much more easy to solve than the ones in the DNN. But the advantage is you have a very clear structure of what this optimization problem looks like. And so Illia went ahead and said, can I find a numerical approach to solving this problem that's efficient, rather than using stochastic gradient descent? And he did. And what he did was to say, let me look at an operator splitting method where I freeze 3 of the degrees of freedom and only solve for 1 of the remaining ones, and then I let that loop through the 4 degrees of freedom. Turns out, for solving for W, S, and lambda, the problem is exactly solvable. Wow, no iteration, no nothing. You write down the solution, you program it, call the function, you have the solution for each of these individual problems. Finding the gammas is not analytically solvable, but it's a convex optimization problem. So there is very efficient methods for that available. If you're willing to make one more approximation step and say, let me replace this expression here by another function that I know is an upper limit, an upper estimate of this rigorously. So I replace it by a function that's definitely bigger than this one, bigger or equal. Then I minimize the new problem. Then I know the minimum of the new problem will definitely be maybe a bit bigger than the result I'm really looking at, but I'm on the safe side. If you are willing to do that, then turns out you use what is called Jensen's inequality. It's actually easy if you have a convex function, right? Like that. You put a tangent, then you know the tangent is always below your convex curve. That's Jensen's inequality. You replace the nonlinear function by a straight line, essentially, right? So you do that, and then even the gamma problem is analytically solvable. So now you loop through calls of analytical solutions to your subproblems. Turns out the method converges second order like the Newton method. Extremely fast. And we can see that in data. And then actually there is in the sense of informatics, there is a complexity estimate, and it turns out in this version of the method, the complexity is comparable to the established algorithms for solving the k-means clustering problem. That's one of the standard clustering mechanisms, and it's the cheapest you have in machine learning toolboxes, but it cannot do more than clustering. So it doesn't do any of the learning, etc. So anyway, so it's comparable to the cheapest algorithm we have in class. Good. Right now, okay, suppose you have learned WS and lambda. Forget about the gammas, those were only needed in order to train the other guys. Now you get a new point X, new data point. You basically find by a projection in your simplex, you find the convex combination weights that go with this point. You convex combine the lambdas that you have learned with these new data convex combination weights, and you have your prediction. So once you have all this, evaluation is a piece of cake. And here's examples. So for this problem of El Niño prediction learning, Illia compared a whole lot of machine learning tools that are available in the MATLAB toolbox. And he used the MATLAB toolbox because he said, okay, those are pros. When they issue a part of the toolbox, they have tested it well, I can rely on that, but I'm not able to follow each and every of the newest papers in machine learning and implement that myself. So therefore, I need to rely on what's available on the market. And he does that each year, he updates to the newest toolbox, and then so he goes. But at that time, this is in 22, he had a number of beasts available, and then he had a plot where he looked at model complexity, which is essentially in the sSPA method, it's the number of reference points that you allow for. And in the, for example, DNN, it's the number of neurons that in total you allow for. So that increases the number of parameters you have. That's the model complexity. And then here is a measure of the accuracy of your prediction, and it's the area under curve measure. It's essentially when it's 0.5, your method says correct as often as it is wrong. So basically you have no result. The closer it is to unity, the closer you get to each time I have a correct prediction. That's qualitatively what it is. Why area under curve? That's an interesting aspect too. Each of these machine learning tools, just like this one, I didn't tell you about it yet, has some leftover free parameters. This is the weights of the penalties here. And typically there is no theory for determining those. And what people do in the machine learning field, and Illia did the same, is to say, let me assume a reasonably broad range for these three parameters, train my model each time, and then check for each of these samples, check the level of accuracy of my prediction. And then take under the quality curve in the 0, 1/2 versus parameter values plot, you take the area under that curve of quality. This is basically your quality measure in the end. So you try to capture how robust is your method in total, even if you have uncertainties in these parameters and you jiggle with them a bit, do you still get reasonable answers? That's what this area under curve quality measure means. And there's 4 contenders that are at the level of beyond 0.8, which is the sparse generalized linear method. Then it's the support vector machine. It's the best deep learning tool that Illia had for this problem in the MATLAB toolbox. And they are all living up here. And the sSPA is the dotted line over here. So in a sense, you have 4 contenders here that are competitive. But when you go to learning costs, and you again plot that versus model complexity, you find out that the 3 other ones that are in quality up here, they cost about between 500 and 5,000 times as much as the sSPA method to train. And this is for a problem with 200 degrees of freedom. If you go to 1,000 or more degrees of freedom, which is very often done, the gap becomes ever bigger. That's because these methods, they converge first order, this method converges second order, and this is the whole story of the Newton method, why it is so successful and efficient. So it's very efficient to train. And in fact, they tried it on a million degrees of freedom problem, and the difference between training was Illia could do it on a laptop, and with the other methods, you would have to use a huge computer, the high performance computer at the Swiss center. I don't know what the name is. Anyway, so this is complexity and accuracy. Here is an interesting plot on the right. This is our 200 degrees of freedom. The first 100 is the sea surface temperature, EOS. This is the ocean slice, EOS. And this is the WDs. This is the weights we have been talking about. Right? And what you can see here, you don't throw away any of them, you keep them, you try to see is there any influence I can find, but the influence of most of them is actually very weak. You have about 16 modes that are beyond 0.01 here. Aha! Out of 200, it seems only 16 modes seem to be important. And so Illia did that test, the one I mentioned to you, Carsten, earlier. He said, let me throw away everybody who has a weight less than 0.01. and take only the remaining degrees of freedom, retrain the method, see what I get. And he basically gets the same results. Now that is really important because the EOFs, and in fact what they did was they took EOFs in over 1 day, so 4 observations of the EOFs as a short time series. These little patterns, you can look at them, you can interpret them as a theoretician, and you can try to find ideas of why the heck is this particular pattern of sea surface temperature important for creating an El Niño or not. So it tells you what are the important degrees of freedom in that sense. Now that's another piece of insight that you don't get from neural networks. So the dimension reduction, first to reference points, then in the weights here, is very clear and transparent how it comes about, and it gives you information of how behind the scenes the method has managed to sort out what is important, what is not, and then learn a function on the rest. Yes?
These coefficients of anything with eigenvalues.
Oh, I don't hear very well. Can you repeat?
You get the matrix, you get some eigenvalues, and they have some size distribution.
Yes.
Do they have anything to do with your weights?
Thank you. Very good question.
Very far away.
The sequence here is actually the usual importance of EOFs. So for the sea surface,
Nothing new you get with your, say, additional channel information, where you have added up. You see, you have three. You wanted to have a penalty on the
weights.
probability of the weights, and still you get more or less the same weights as if you just do a single value.
You're asking whether there are cases where that is happening, or here we obviously don't get the same weights. Oh, you mean after he has thrown away all the rest?
Oh, yes.
Oh, the data I haven't looked at. What I know is he told me when he threw away the other degrees of freedom, the method basically gave him the same function in terms of what the output was. Yeah. Okay. What did I want to say? Yeah, I misinterpreted your question, but that gave me a trigger to give you an answer to this one. So the sequence here is actually the leading first, second, etc. EOS. So you sort them in importance in terms of the singular values. And you can see that the second, third, and fourth are really the ones with the big amplitude here. The leading one isn't. And here in the ocean deep slice, it's actually very different. So it's not at all that the leading EOFs are the ones that seem to be important for the learning process. It's higher modes that come up and seem to have an influence. Terry is working on it, as far as I know, but I can't.
Somehow will just produce this. You have the middle term, you have 3 terms, and the second term with the Shannon information.
Yeah.
Will do that or not?
The Shannon.
You see, if you have three vectors, you see?
Yes.
And you sum it up. And this is the middle term, which just will produce this different weight for this different.
It controls how the weights are allowed to spread.
And this is this, if I will omit this, I will get similar.
It's not clear what happens in that case. My understanding, this is intuition though, I haven't discussed that in detail with Illia, but my intuition is that if you do that, the solution to this problem is probably not unique. You can run easily into finding only this or finding only that or finding only 2 of them, but you don't have the information forcefully spread to collect the information from all the degrees of freedom. Yeah. Okay, this was that. And then there's one more example that I want to briefly discuss. It's a nonlinear example in the sense that we have 2 spirals, the Swiss roll problem from Haber and Ruth Otto in 20-something. And the idea is you give these data points labeled with red or blue to the machine learning tool, and then you give it a new point, and it's supposed to tell you is it red or blue. Okay, so give you like a decision function. And so when Illia did that with 2 turns of the spiral, and he compares the best neural network tool that he found for this problem in the toolbox with the best boosted random forest tool, that's a different method. I don't even know the details, but that's supposedly also a contender in this field. And then you look at the eSPA method, the AUCs are all very close to 1 or even exactly 1, so they catch this very well. But if you keep the same number of reference points or degrees of freedom, no, it was different. What was kept? Something else was kept between this. It's got to be to do with the parameter numbers, 1500, 1500, this I think was what Illia took. He took the number of parameters from both methods and then took a comparable number in his scheme to compare with the one that has the lowest number of degrees of freedom. And when you do that for 4 turns, you can see that the neural network isn't able to identify a spiral anymore. The pattern looks very different. Right? The one color here is blue and the other color is red, as you can see here, right? And it doesn't see the pattern, and the boosted random forest doesn't see the spiral either very well. Whereas this method simply, this is a little twist. When you switch from the original penalty term for the approximation of the probabilities, you switch to Jensen's inequality, you do not get piecewise linear on simplices anymore, but you get piecewise constant on the dual cells, on the Voronoi grid. And this is what you see here. So on the Voronoi grid, around this reference point, you have piecewise constant data. And this is still a 0.98 quality, and they have decayed quite a bit relative to that. And there's more stuff to discuss, but the take-home messages I have is in the geosciences, many of the applications I hear about now in the geosciences are all small data problems, and one should be aware of that. It's not big data problems. Then popular deep learning, etc. tools might not be the best in high dimensions. If you have the wrong function with completely different information to subregions of space, you might actually have a problem that's very, very expensive to do with neural networks. Then I find it important to say that in the face of the fact that we are dealing with small data problems, the function approximation is not a statistical problem, because you can do meaningful statistics only when you have a lot of data, as we explained with the regression straight line in a 2-dimensional cloud of points. Only if you have many data points relative to the few degrees of freedom of your straight line can you do a meaningful error estimate and be sure you're getting something meaningful. So that's not the case here, systematically not. So it's not a statistics problem, it's an approximation problem. You have to approach it from the point of view, mathematically speaking, of approximation theory. How can I catch functions that live in high dimensions on weird manifolds? What is a systematic good way to capture them, get more, as much information out of it as I can when I run this, and get the domain of the function as we go. Anyway, then I learned a lot by just reading up on information theory, Shannon entropy. The last term was called the Kullback-Leibler divergence of probability distributions. I haven't gone to speak about it, but I learned a lot, and I recommend very much whoever is in this field and tries to do machine learning stuff, information theory is something very good to know. I just recommend that. And then if you are, and you have your problem written down that you want to solve, it's a good idea to look into analysis, numerical analysis of the problem, because that can help you a lot in solving it efficiently, as we have seen. And with that, Here's a couple of references. I will leave the slides with the organizers here, with Jennifer. So whoever is interested. I also have a couple more slides with details on entropy, Shannon entropy, Kullback-Leiber, and what have you, if you're interested. And this is the end of it. Thank you very much.
Thanks a lot for these thoughts on machine learning. I have one quick question. You forgot to mention if this, whether this method which you want to sell here was actually doing a better job in predicting El Niño at the end.